Combining like terms. When we talk about combining terms, we really just mean adding or subtracting them. So over here I have two expressions, an expression 8 plus 3 and another expression 8 minus 3, very simple expressions, and each of these expressions has just two terms, 1, 2, 1, 2. And the word combining is just a fancy word for adding or subtracting. So I can combine these terms very easily. In this case, they're getting added, and you already know the answer. Over here, I'm going to get 11. And over here, I can also combine these terms, and in this case, the 3 is being subtracted from the 8. And I'm sure you know the answer for this also. 8 minus 3 is 5. So these are two very simple examples of combining like terms. Like terms are terms that have the same variables raised to the exact same powers. So I wrote a bunch of terms out. In this case, I just separated all of the terms with commas. So this is not one long expression. In an expression, the terms would be separated by plus signs or minus signs. I just have a bunch of separate terms here. They're not in an expression, and each term is separated from the next one by a comma. And I want you to take a look at this and try to ask yourself which terms are like terms. And remember, terms are like terms if you see the exact same variables and those variables are raised to the exact same powers, meaning the exact same exponents. So take a look at that for a few seconds and see if you can spot which terms go together, which terms are like terms. Alright, so let's start talking about which terms are like terms. We'll start with the first one. This term over here does not have any variables whatsoever. So we're going to look for any other terms here that do not have any variables whatsoever. This term over here, even though the coefficient here, 43, is exactly the same number as this number, this term has an x squared in it, whereas this term does not have any variables at all. So although it might be tempting to think that this term is a like term with this one, these are not like terms, even though you do see the same numbers here. Actually, this term and this term are like terms because both of them do not have any variables. So I'll just go ahead and link these terms together. Alright, let's move on to the next one. We have x squared. In this case, there's no coefficient. A coefficient is just a number that comes in front of the variable. There's no coefficient here. You could, if you wanted to, write a 1 in front of there. So x squared is the same as 1x squared. But I just wrote it without any coefficient. But that doesn't mean that it can't have any, a like term to go along with it. Do you see any other terms here that have x squared in them? And actually there are a few of them. Let's see. So this one has x squared, this one has x squared, this one has x squared, and this one has x squared. Now all of those terms except for one of them are like terms. Can you guess which one does not go along with the others? It's this one right over here, and the reason is because this term has that other variable d in it. So this term does not go along with these 4 other terms. So let's circle those 4 other terms. This, and this, and this, and this one. These 4 terms are all like terms, so they can be added or subtracted with each other. Are there any other like terms here? What about this one right over here, 10x? There are all of these x's all over the place. X, 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 X. Is this a like term with any of these? The answer again is no. And the reason is, this is just a plain x, whereas all of the other x's that you see in all of the other terms have an exponent above them. So this is x to the 2nd power, or x squared. This is x to the 3rd power. This one does not have any exponents. So none of these other terms are like terms with 10x. What about these d's here? We have 10d to the 2nd power, and here we have 17d to the 3rd power. So we have the same variable here. Unfortunately, these are different exponents over here, so these also do not go together. But there are some more terms that do go together. Actually, this one over here is a like term with this term over here. They both have d to the 3rd power and x to the 3rd power. Alright, so these also would go together. Alright, and so I believe that's it. Now you might have noticed that in this expression, in this term, the d came before the x, whereas in this term the x came before the d. That's okay, as long as they both have a d and an x, and the exponent above the x is the same in both of them, and the exponent above the d is the same in both of them, then they're still like terms. I don't want to give you the impression, actually, that the exponents within the terms have to be the same. Let me just give you another example. If I were to say, let's just do 7d to the 4th power, x to the 8th power, and 42 x to the 8th power, d to the 4th power. These would also be like terms. Okay, so the exponents above the variables inside the term do not have to match, but within the terms they do have to match. So here I have x raised to the 8th power, and here I have x raised to the 8th power, and here I have d raised to the 4th power, and here I have d raised to the 4th power. Okay, let's move on. Only like terms may be combined. So I wrote a bunch of equations. I wrote 4 equations on this page, and I put question marks above the equal signs because I want you to look at these and ask yourself if you think that they're true. 2 of these are good equations and 2 of them are not. Right? So we're going to figure out which one of these are actually good equations. Is 3x plus 4x really equal to 7x? Is 3x plus 4x squared really equal to 7x? Well, how can we check that? Basically, this means if I take a number and multiply it by 3, and I take the same number and I multiply it by 4, and then I add those, whatever I get, I add those together, is that equal to taking that same number and multiplying it by 7? So at home, you can try plugging numbers in for x for all. Just think of any number you want and plug it in for x and see if you always get the same thing on the same side. I'm just going to do it with one number, and I'm just going to pick an easy number. I'm going to pick the number 5. So what I want to find out is, let's look at the first one. If I plug 5 in everywhere I see an x, do I get something which is true? So is 3 plus 5 plus 4 times, did I say 3 plus 5? 3 times 5 plus 4 times 5 equal to 7 times 5. Well, let's see. This is 15 plus 20, and 7 times 5 is 35. So is 15 plus 20 equal to 35? 15 plus 20 is 35, so I get 35 equals 35. Yes, that's good. Alright, so, and from the last slide, you know that 3x and 4x, they both have the same variable, and they have the same exponents, or in this case, they each have no exponent. So these are like terms, which means we can combine them, which means we can add or subtract them. And you can see, so 3 plus 4 is 7, so 3x plus 4x is 7x, and you can see from all of this that it does work out. What about these over here? Here I have 3x to the second power plus 4x to the second power. These are also like terms, because both of them have x to the second power. So we should be able to add the 3 and the 4 and get 7x squared, and this should really be exactly the same as this if we plug in some number for the x's over here. So let's do the same exact thing we did before. Everywhere I see an x, I'm just going to plug in the number 5, and I'm going to see if both sides of my equation are really true. So we have 3 times 5 squared plus 4 times 5 squared. And I'm just picking 5 here because it's an easy number to use. You can use any number you want. Equals 7 times 5 squared. Is that true? Well, 5 squared means 5 times 5, which is 25. So I have here 3 times 25, which is 75. 4 times 25 is 100. And 7 times 25 is 125. So on the next line, I'm going to write 75 plus 100 equals 175. And 75 plus 100 is 75, so I get 75 equals, 75 plus 100 is 175, so I have 175 equals 175, so yes, that checks out. Right? Will it work over here? 3x and 4x squared are not like terms, because this term is the x is raised to the second power, and here the x is not raised to any power. Or you can actually think of that as being raised to the first power, but nobody really writes a 1 over here. You could write a 1, but nobody does that. So these are actually not like terms. So is it correct for me to say that 3x plus 4x squared is equal to 7x? If these are not like terms, can I still go ahead and add the 3 and the 4 and get 7? Well, let's see. Again, I'm just going to use the number 5. So I have 3 times 5 is 15. Pretend that I'm plugging a 5 in where I see the x. And then I have 3 times 5 squared. Well, 5 squared means 5 times 5, which is 25. and 25 times 4 is 100. So over here, I'm going to get 15 plus 100 equals, now again, if I pretend that this x is a 5, I have 7 times 5 equals 35. Again, you could use any number you want. You don't have to use 5. I'm just picking 5 as an example because it's an easy number to use. And so we get 15 plus 100 is 115 equals 35. Is that a true statement? No, obviously it's not. Now, what if, I meant to write this in before, I guess I forgot. What if we put an exponent of 2 over here? Would that make this equal to this? Well, let's just see. Again, we would have 3 times 5 is 15. 4 times 5 squared would be 100. And 7 times 5 squared would be 175. So let's see. We would get 15 plus 100 equals 175. So we get 115 equals 175. Again, it does not work, right? So if the terms that I'm trying to combine are not like terms, I'm going to get something that doesn't make sense. Okay, I cannot just go ahead and add the 3 and the 4 and say that that's equal to 7 if this term has an x and this term has an x squared. I can only add or subtract terms when they are like terms, meaning that the terms have the same variables raised to the same exponents. Let's finish off the video with combining like terms in a giant monster expression. So the first thing we're going to try to figure out is which terms are like terms. Remember, we're looking for the same variables raised to the same exponents. Here I have a j to the third power. Here I have a j to the second power. So these terms are not like terms. We cannot combine them. Here I have another j to the third power, so I can combine this term with this term. And what I like to do is I like to underline the terms that are like terms. I want you to notice something here. I'm underlining the term with the operation also. It's very important that you do that to remind yourself that you have to pay attention to this operation. I know that a lot of students will ignore the operation that's in front of the term. Don't ignore it. It's there because it matters. Okay? Are there any other terms which I can combine with these terms? You don't have to stop at 2. If there are more terms which are like terms, you can throw those in. Now we see, and this has j to the third power. But it also has b to the fourth power, so this term is not a like term with the other two. This has j to the second power, so actually this term and this term are like terms, so let's go ahead and underline those. Notice I'm underlining it. I'm including the operation that's in front. I don't want to just ignore that. Do not ignore that. What about this j to the third? That will be combined with all of our other j to the third terms. And now we have another j to the third, b to the fourth. Just like this over here, j to the third, b to the fourth, so we can combine those. All right, now let's just work all of this out. So we have -2 minus 3 is -5 minus, wait a minute, what's here? if you do not see a coefficient in front of the variable, that means that the coefficient is 1. You can write it in. Let's just write a 1 in here. And actually, while I'm at it, I'm just going to do it with the last term also. There's a 1 in here also. If you do not see a coefficient, the coefficient is 1. So let's start that again. We have -2 minus 3 is -5, minus 1 is -6. So we have -6j to the third. Now what else do we have here? We have a 4j squared. There was a plus sign in front of it, so we're just going to think of this, we're just going to say to ourselves, we have positive 4j squared minus 10j squared. So 4 minus 10 is -6. So we're going to get another -6, but this time it's j squared. J to the second power. Squared is just a fancy way of saying to the second power. And finally, we have a positive 9. Remember we wrote this 1 in here because there was nothing in front of this to begin with, so we wrote the 1 in. So now we have 9 minus 1 is 8. 9 minus 1 is positive 8, so we're going to put a plus 8. J to the third, we're just copying the variables and the exponents from the terms. J to the third, B to the fourth. Alrighty then, that's that. Have a great night.